Hi, I'm Vincenzo Coya, and welcome back to Stat545, Part B, the video series designed to help you write a clean and modern data analysis. I gotta tell you something. When I was writing my analysis for my dissertation, I had gigantic R scripts that were just horrendous to look at. And of course there were errors everywhere throughout the script. And fixing even one small error meant I had to go through the entire script to make sure that everything worked again. And of course, every time I ran the script, I'd get something different. The key to fixing this problem is to recognize that each analysis has its own unique vocabulary to it. A set of actions that, when strung together, form a nice tidy story to your analysis. And how do you make this vocabulary or this set of actions? You make functions. And that's what today's topic is about, how to make functions for a data analysis. Today we have 3 practices that will help you develop functions for your data analysis. The first practice is to bundle important calculations into functions. Now, as you write your analysis, you'll probably notice that certain calculations come up frequently.
As a simple example, here's a vector of areas of the largest land masses in the world. And for this analysis, both the mean and the median are important, and the difference between these two values really matters to me.
Now, realistically, I'm not just going to do this calculation for the islands dataset and that's it. Chances are I'll have a bigger dataset where I'll want to do this calculation for different parts of that dataset, as well as that dataset gets processed throughout the analysis. And if you type out this calculation every time, you're probably going to make a mistake many times. Instead, move this calculation into a function and remove the context of the analysis from this function.
Let's call the function mean minus median, set up the framework for defining a function, and now let's put the calculation inside of the function. Since the islands dataset is specific to the analysis, we'll replace it by x, representing some generic input, and place that in the list of function arguments. Let's try out the function on our islands dataset, putting the islands dataset in place of x. Now we can calculate on more than just the islands data. Remember the penguins dataset? It has data collected on 3 penguin species across time. Let's try applying the mean minus median function to the body mass for each species in each year. It looks great. The functions seem to have worked on different inputs, but there are missing values. This is because the mean and median functions, by default, return NA if any input values are NA. You might then think it's a good idea to remove NA values in both the mean and median functions using their na.rm arguments. Although it will work, it's not a good idea, and this brings us to our second practice for making functions.
The second practice is to generalize your functions by removing magic numbers. Now, at the time of writing your mean minus median function, you might think that you will always want to remove missing values. So why not just hard code that decision into your function? Any decision that's hard coded into a function is called a magic number. And these are harmful because when you make them, you're thinking only narrowly within the context of your analysis at that specific time. But chances are your function will be used in a different context and maybe even by somebody else. So why force that decision on them?
Instead of hard coding true, make that a second argument to your function so that anyone using your function can indicate their preference. Now we can remove missing values when calculating on the penguins dataset by specifying na.rm equals true. But there's still one problem. You now must specify na.rm every single time you use the function. This means that our original calculation on the islands dataset won't work as is until we indicate what na.rm is. That's pretty inconvenient. Because serving our users is a top priority when making functions, let's specify a default for the na.rm argument. Let's stick with false, the default that the mean and median functions use. Now the default is used whenever we don't specify this argument.
Now, does this mean that every argument that shows up in the mean and median functions should also show up in your own function? This can get pretty overwhelming if you're using a function like lm that has a lot of arguments to it. But luckily there is a workaround using the ... or the ellipsis argument.
Just put the ellipsis as an argument to our function, and then place the ellipsis in the mean and median functions. Now, specifying anything that's not the x or na.rm arguments will be passed to the mean and median functions. In this case, trim equals 0.1 is passed into the mean function, which recognizes and uses this input. Trim equals 0.1 is also passed into the median function, but according to the documentation, median doesn't recognize an argument named trim, and so it gets absorbed into its ellipsis, and in this case, goes unused. This means that we could also use the ellipsis to absorb the na.rm argument. Although the computer doesn't care, you'd be serving your human users better by including it as an argument, because it presents them with a decision in case they're wondering what to do if they're getting na.
And just a warning, don't get overzealous in your quest to generalizing your functions, because you can overdo it.
Why not generalize the mean and median functions and call them function 1 and function 2? After all, aren't they hard-coded decisions? Nope, because the purpose of the function is to take the mean minus the median. It's even baked right into the function name. And plus, that would pretty much render the function useless.
As you generalize your function, it's important that you provide documentation for the function so that you can best serve the users of your function, including yourself.
We'll cover formal function documentation in episode 3b, but for now, at a minimum, aim to describe what your function does, what all of the inputs are, and what the output is.
Third is to test your function. Now that you've built your function, we need to make sure that it works. Now we've already done this informally by experimenting with the function on the islands and the penguins dataset, and we saw that the output looked sensible in those cases. But we really need to test the function against a variety of inputs if we want to gain any credibility and confidence in our functions. And on top of that, we need to formalize these tests so that we can rerun the tests if we ever modify the function or change its dependencies.
For example, I happen to know that the mean and median are equal for symmetric data, and so should give me 0. Looks like it worked, but it would be nice if we didn't have to manually look for a 0 every time we run this test. Instead, it's helpful to use the testthat package. I can now explicitly state that I'm expecting the output to be 0. There's silence if the test passes, and an error if the test fails. There are many expect functions at your disposal. This time, I want to test whether another output gives a positive value, so I'll use the expect_gt function for expect greater than. I happen to know that for right-skewed data, the mean is greater than the median. So our function should give us a positive value. It would also be wise to check that the function handles missing values properly, removing missing values in one case and keeping them in another.
Okay, so your function seems to be calculating correctly. Now it's time to attack your function. Try putting in nonsense and see if your function handles the situation correctly.
I hope to get an error if I input a logical value, but I don't. This is easy to fix. Just have the function throw an error if x is not numeric. Just make sure to write an informative error message. Now I get the error I was looking for. Sure enough, there's an expect function that's just what we need. It's a good idea to continue writing tests for other types of input. Well, I think I'm happy with all the tests that I have for now. I can always add more later, but for now they all work. The only real problem now is that it's hard for someone to know what the purpose of each of these is. It would be nice if we could group these first three, for example, as testing based on the data's skew. A convenient way of doing this is with the testthat function. Its first argument should be a description of what you're testing, continuing a sentence that starts with testthat. Its second argument should contain the related checks. As in the expect functions, the testthat function returns nothing if the tests pass. Continuing along, we might want to make two other groups of tests, resulting in a much more readable and workable collection of tests.
Of course, we can't check that your function works for all possible inputs, but we can at least try for a variety of inputs. And by the way, the testthat package is the de facto standard for testing functions, and most of the R packages that you know and love use testthat to test their functions. Well, these three practices should be enough to get you started with writing functions in R so that your code can be more robust and readable. I think the trickiest part now is in deciding what collection of functions you should make to form a vocabulary for your analysis. This will come with practice, but as you keep developing your analysis, don't be afraid to change your functions. Don't be afraid to make functions that depend on other functions. But ultimately, just make sure that your functions are small and don't do a whole lot. In summary, bundle important calculations into functions, generalize your functions by removing magic numbers, and test your functions. I hope you enjoyed today's episode. Join us next class where we discuss per and list columns. And don't forget to subscribe to this channel. I really want to help you write a clean and modern data analysis, and subscribing is really the best way for you to keep up to date with these videos. See you next time.